Hello, everybody. I hope you can all hear me well. The sound is not too loud. It's okay? Yeah? Cool. So, hi, everybody, and welcome to this workshop, which is titled Building Agents with LangGraph, from GPT to RAG and multi-agent systems. We are super thrilled to have the opportunity to present this topic to you. As you can see, we have a lot of different subjects to cover today. So I hope you are ready and that you will be able to learn at least a few new things today as well with us. Before we dive in, just a few quick words about us. So my name is Gaëtan, and I'm here today with Victor. We are hosting this workshop today for you. We are both working as machine learning engineers at Visium. If you're not familiar with Visium, we are a machine learning consulting company. We are primarily based in Lausanne and Zurich, and we also have an antenna in Valencia in Spain as well. Our mission is to enable other companies in their data strategies, helping them design their AI programs, scope projects, and ultimately realize these projects with the help of our team of data engineers and ML engineers, of which you can see a small sample today. So I hope you are lucky for that. Now for today's content, we will start with a brief introduction to the topic, explain why we think that we should care about agentic AI in general and why it will be very impactful in our future. We will then try to define a few more or less theoretical concepts behind agentic AI, so we can all speak the same language today, and give you a few illustrative examples of agentic systems that have been developed recently in research. Afterwards, we will have two hands-on sessions today that are planned for you. In the first one, we will go through the very basics of LangChain as a framework to help you get started with it and build the first simple RAG system. After this session, we will try to catch a small break so everybody can recharge. And then we will go to the bigger piece of this workshop, which will be the implementation of an actual multi-agent system using LangGraph. Finally, we'll have a few departing words, and hopefully we'll be able to finish slightly early today, so we can stick around with Victor at the end for extra questions if needed, discuss with you if you are interested, and then you can also get the first in line for lunch, so that would be great. Without further ado, let's get started. Victor, if you want to take over.
Yes. So what is agentic AI and why are we interested in it? So in recent years, we've seen transformative changes from generative AI. Agentic AI goes a step further. It's basically focused on action and independence of agents. What we call agentic AI are systems designed to act autonomously that can plan and perform actions to solve the requests of the user with minimal supervision. The advances of Gen AI basically serve as a basis for agentic AI to empower autonomous systems that are independent in these decision-making and actions. So this is a fast-changing field. The vocabulary used changes also a lot, so we'll go through a few words that are used when talking about agentic AI so that we can all be aligned on these semantics before going into the workshop. In December, Anthropic published an article called Building Effective Agents, where they define more clearly what they call an agent, what they call a workflow, and we'll present that. But these are not hard definitions. This is a suggestion that we think is valuable to present, but the words can be sometimes used in a different context. So first we have the LLM and augmented LLM with tools. So I think everybody is probably familiar with LLMs and how they usually work, where you make a request to the model and you get a generated answer from it. So an augmented LLM is an LLM that has access to tools. So that can be, for example, document retrieval, web search, code execution. And the idea is to give independence to the model in deciding how to use these tools. For that, you need to give information about how it works and what it will return. And then you leave it to the model to decide if it wants to query the tool when you ask the question to best answer it. So what are workflows? Workflows are basically agentic systems, according to Anthropic, for example, where the steps are predefined, where we have a very clear idea how to split the task. So this is interaction between LLMs that can have tools also, but the flow of information basically is clear in general for these tasks, and that's what workflows are mostly used for. It gives control, predictability, and consistency in the solving of the task. Also, I didn't have a very good image to illustrate the general concept, so I know Gaetan doesn't like this one. If you've got any suggestions, please let us know. So we'll give a few examples of workflows so everybody can have a better idea what these mean, what these represent. So a very simple one would be prompt chaining. Prompt chaining is basically when you do multiple calls to LLMs. Again, those LLMs can have access to tools or not. And this is particularly well suited to tasks where you can define the more complex goal in terms of simpler sub-steps, basically. You can also add some logic in it. For example, if you're not satisfied with the first steps, you can stop execution, or you can sometimes recover from it by rerunning initial steps. A basic example, for example, would be instead of generating documents in a multitude of languages, you could generate a base one for your use case and then ask a following model to translate it in different languages for you. And this will in general take a bit more time than doing a single query, but will help improve the quality of the output. So another example of workflow would be routing, for example. This gives a bit more control, a bit more freedom, and flexibility to your system. So routing, you can ask, again, your system to solve a task, and you give the ability to the, in this example, first model to decide to what subsequent model it wants to send the task. So you can have very specialized LLMs. And when receiving, for example, a client request or a ticket for helping clients, again, you can basically move the solving of the problem to your sub-agent systems. And that can be, again, here you see single models that can be specialized, but those can also be more complex workflows themselves. You can then go a step beyond that, and you can have multiple executions in parallel. And for these executions, again, you can have either hard-coded tasks, so for example, specialized LLMs or general LLMs with a specialized task that is given to them, for example, through a prompt. And you can also have the flexibility to generate multiple ones at runtime. So if you have, for example, in this case, an orchestrator, you can ask it to define tasks based on the request, and on the fly create submodels that will be distributed the tasks that you want to solve. And once these parallel runs are done, you can have synthesizer model at the end that will take the output of all of your models to create a final output for the user. This is the use case that we'll be working on today, later in the session 2 of the workshop. Another case would be evaluator optimizer. So this is an example of a loop you can have in your workflow. This one is very simple, so you have those two models interacting back and forth. You can have complex systems where the loop is not between two models, but can be a bigger loop in a bigger system, bigger workflow. Here, as you can see, a very simple example, practical case, would be, for example, the first model generating code and the second one making some comments and feedback until it is happy with the result and think it can be submitted as final output. So with all these examples of agentic systems, workflows in this case, we can see that some tasks can be well defined in terms of discrete steps, even when we have some flexibility, for example, in the number of workers who are generating during the solving of the task. And what Anthropic in their article call an agent is, in this case, as you can see, like a single model, for example, with access to tools that can interact with the environment and whose goal and dynamic is basically to understand, take independent decisions on the fly, and this is well suited for more complex tasks that we cannot define in terms of separated steps. So they offer more flexibility. That can be, for example, if you want to book some holidays and you need a system that can go on the web and adapt to any kind of web interface or make a request for a plane ticket, then navigate a hotel booking website, for example. So this is more difficult to define a priori in terms of the nodes that you saw in the graphs before, that are the workflows. And this gives a lot more flexibility to the model. This is also a bit more complex, and you have less control and less repeatability in the actions that are taken. So in this workshop, we'll use the term agent a bit more loosely. So in the notebooks that you'll see, we use agent for any LLM part of the workflow system that has a given task assigned to it through the prompt. So Gaëtan will now give a few examples of applications of these agentic systems.
Thank you, Victor. Maybe just until now, if there are any questions in the audience regarding theoretical concepts that were briefly introduced. It was quite fast, so just in case. Feel free to raise your hand. We have a mic in the audience. Yeah.
Can you talk about the various type of orchestration? I understand, you can let it run a bit randomly. You can be sequential. Any experience with, the various type of orchestration?
Yes. So all these examples, the goal is to give an idea of what's possible and what is usually used as construction blocks in workflows. But sometimes the difference between the systems is a bit blurry, and those are not strong concepts. So you can have some overlap between them. Orchestration, for example, you could have either predefined worker nodes. So that would be what people call more parallelization, where you already know how you want to parallelize the task, but you can have the workers being defined on the fly by the orchestrator that, given the request, will itself decide on the subtasks that needs to be accomplished to answer it, and will generate and send these requests, these subtasks, to the agents. I don't know if this answered the question, or you wanted more concrete examples?
Yeah, I guess maybe when we get into the details, I think what I'm looking for, to understand throughout the day is where do you put the autonomy? Is that in the way you define the worker, or is that in the way you manage the orchestrator?
So, again, these concepts are very flexible. So this is just to give an idea. It does not need to be taken as ground truth. So, for example, here you could imagine the worker being itself a completely independent agent, as presented in the last slide about agents. One of the, but we'll see that in more detail also in the notebooks. But you can, for example, leave it to the orchestrator to define the responsibility of each of the subsequent models, the worker models. But those models you can also define quite freely into how you want them to solve the task. So they can have access to tools. They can themselves send tasks to other models. And the idea is to have this communication flow, this workflow more or less defined, but you have a lot of flexibility into how well you want this to be predefined or defined on the fly. And again, this example will be explored in the notebook, so maybe it will give more insights.
I guess so. So flexibility. Okay, thank you.
Yes. Any other questions?
All right, so then let's dive in a few quick illustrative examples of existing agentic workflows that have been implemented quite recently. We cherry-picked just 3 of those examples to showcase how research in agentic AI is evolving and exploring new grounds as we speak in terms of human-computer interaction. This first example is from a 2024 paper from Stanford University. It's named the Virtual Lab. And the idea is to have the human operator only designing one or a few very simple agents by specifying only very basic information. So the human user will create an agent that is, for example, here the principal investigator by specifying their title, their expertise, what is their goal on the project, and what will be their role on the project as well. And then they give this principal investigator the task of handling the research project for them. And this principal investigator has all the power that it needs to recruit other agents in his team. So by recruiting, we mean instantiate worker models. So it has the flexibility to create its own team by leveraging the prompting of new agents, using, again, the same simple information, such as title, expertise, goal, and role in the project. And then these agents will more or less self-organize, led by, again, the principal investigator. And they will organize, for example, small meetings where each of the agents will talk next to one after the other, share information based on their background and expertise. Maybe they will also have access to specific tools if needed. And they can take decisions and decide on the next task to achieve in the project according to these little meetings. Then they will also create, for example, sub-teams where a few of the little agents will work together on solving specific tasks, such as, for example, creating simulation environments or writing code to compute whether nanobodies are going to bind to the antigen or not. And they will iterate together, giving each other feedback based on their different backgrounds. I think this really showcases, again, what we were talking about with the previous question, the flexibility of these multi-agent workflow, as well as their ability to self-organize. So here we have what is really defined by the user is only the main principal investigator agent, but all the rest is being generated on the fly by this new agent. Then we have a second example, which is again another Stanford paper, but this time from 2023. It's here, okay. So there's a little video that I can play for you. Maybe I will put it full screen so we can see it better. All right. So as you can see, we are here in a little video game simulation, and we are met with a little village. And in this village, we have a lot of little characters, which are non-playable characters, so NPCs for short. And these non-playable characters are, in most video games, following some very procedural logic that has been implemented by the programmers. In this case, there is something a little bit different, a bit of a twist, is that each of these NPCs is a little agent of its own. And they can all interact and they're together with the player, with their environment. You can see them here walking and minding their own business, doing their own little tasks. They all have their own background, their whole memories, their objectives for the day and what they want to accomplish. And so what is quite interesting is that they go through this loop here of perceiving their environment. Then they get the perception into this memory of them. and based on their memories, their previous plan, and how they are reflecting on what they are doing, they will decide on the next action to perform. And they will each do that individually using their own little agent system. Now, the interesting part of all that is that the study have shown that human evaluators were also judging that the AI agent controlled NPCs were showing more believable behavior than actual human playing the NPCs behind the scene, which is quite surprising, to say the least. They also showed that each of the little parts, so reflection, planning in advance, interacting with the environment, all allowed the agents to become more and more believable in their behavior. Yeah, I think that's it for this example. Yeah, thanks. Then the third one is a bit more oriented towards text. Here we have a bunch of agents, a team of 10 specialized agents actually, that collaborated together to write a novel of about 300 pages. The topic of the novel, of course, ends up being how the AI rises in our society, and well, I will not spoil the rest to you. But here it's interesting because each agent had a little different role. So some of them were specialized in content creation. Some others were trying to ensure that there was a coherence throughout the story, throughout the character development, pushing for originality by not repeating patterns that were already present in other chapters or even in other novels that are available on the internet. So all of these agents had different roles in the project, and they were interacting together to write this complete novel from scratch. Funnily enough, the whole writing process was also live streamed. So it means you can still watch it back as well, see the models interacting together, giving each other feedback on what they are writing, what they are planning for the development of the character, etc. It's a bit difficult to follow because there are a lot of things happening in the terminal and a lot of things being written. But if you take time to pause the video, you will see that it's quite interesting. And yeah, the whole novel is available on GitHub for free, but it can also be purchased as an actual book. Yeah, so finally, this is just a good example of, again, a workflow, which here is a bit more defined. There is less flexibility in how the agents interact together. But there is many back and forth in this shape of this evaluator optimizer framework that Victor presented earlier in order to reach such a complex level of writing and coherence throughout 300 pages of story. All right, now we'll move on to a more practical part of this workshop. So we'll give just a few intro to LangChain and how it works. We'll see a bit more code, and then we'll dive into the notebook and let you work on some exercises in a few minutes. So for the very basics of LangChain. So LangChain is a framework to interact with LLMs. You may or may not be familiar with it. There are, of course, many other frameworks available, and probably as many good reasons to pick one over the other. Here we just decided to go for LangChain for its simplicity and the abstraction that it proposes, which we deemed were interesting for this workshop. So the very basic of LangChain is to initialize a chat model. So you can use, for example, this chat OpenAI to use an OpenAI model, but you can use other models as well. And you can initialize it by choosing which model you want, which temperature you want to set in the model. So a lot of different hyperparameters that can be tuned. And once you have your model, then you can query it by using this invoke method and passing it a list of messages. LangChain provides you with a bunch of different type of messages. that exhibit metadata, also to understand better the flow of the interaction between the users, the different agents, etc. So you can use, for example, system message to pass a system prompt and prime a model if it supports it. Then you can use human message to actually simulate the user input that we will use when we write to ChatGPT, for example. You have AI messages so that LLM can pass messages to each other. You can use tool messages for when an LLM is requesting a tool and then the tool is sending back a message. A lot of different kind of messages are available directly. Now during this first hands-on part, you guys will implement a small RAG. So maybe a very quick introduction on the concept of a RAG and vector databases first. So vector databases are really the key building block behind every RAG system. To keep it very, very short, the objective is to embed complex high-level data, such as documents or images, into vectors in a compressed format. So for that, we rely on an embedding model that is most of the time pre-trained, and you can use directly from the internet. Or you can also train your own embedding model and fine-tune it for specific tasks if needed. And so once we embed our document, then we store them in a database, and we use the different vectors as an index to retrieve relevant documents based on the proximity with the embedding of a new document or of a query. To perform such retrieval, we can leverage many different kinds of metrics. Typically, cosine distance is used, but you can also use different things. And you can retrieve as many documents as you want. Just some documents will be closer to the actual query and so more relevant to the query you are asking, and some will be less relevant. And in a typical RAG system, what we have is that the documents are retrieved by the worker. So the vector DB sends back a few documents, maybe 1, 2, or 3. And then these documents are used to enrich the original prompt of the LLM by providing this extra information from the document inside the prompt. And then the LLM can generate an answer that is not just generic based on the historical knowledge of its pre-training, but also grounded in the retrieved information from your documents. So this is a typical example of an augmented LLM with a tool. A simple RAG is exactly that. Here in the case of our agentic RAG, it will be slightly different because it can also decide whether a query is relevant or not to perform in the vector DB. If you ask it something that is completely unrelated to the task that it is supposed to do based on this system prompt, it might just say, no, I'm not tasked to do that. So how do we translate that into the LangChain framework? Luckily, LangChain also already offers us a lot of different providers for using vector databases, such as Chroma, Pinecone, and other. In this workshop, we will use Chroma, just for the sake of simplicity. We can then load the documents in a vector store by using an embedding model. So typically, we can use a model provided by OpenAI again. Embed our documents and store them as a vector store. And then when we want to retrieve the actual documents, we need to use this asRetriever method to create the retrieval system. And here again, we can specify how many documents we want, what is the minimum confidence or proximity in terms of which metric. A lot of things can be parameterized again. We will try to keep it simple during the workshop, but you have a lot of flexibility. All right, and then how do we will end up actually implementing the RAG as a tool in LangChain? Well, we just defined the retriever, and now we can use this little syntax that is provided by LangChain using this tool decorator to create a retrieval function, which will invoke the retriever that we created. And then once we have our tool defined, we need to assign it to the LLM to augment it. So for that, we can use the bind tools method. And finally, our base model is now augmented, it's now a RAG model, and we can invoke it to get our response. What it will actually do now is decide whether or not it will perform a call to one of the available tools based on the query that we provided. And then we can perform the call to the tools ourselves to retrieve the documents, enrich the prompt by adding the tool message with the documents that were retrieved, and get the final response of the RAG system. I hope this was clear enough. So now we can get started with the actual coding session. So you have a link to the GitHub repository here on top, bit.ly/amld2025_LangChain. We will show you the repository in a second, but you can open the first notebook and go through the exercises on your own. You will just need to first install the environment using whichever Python package manager you prefer. So pip, UV, or conda, or whatever floats your boat. And then the other requirements that you have is you need to have an OpenAI API key. If you have one of your own, please use it. The running today's workshop shouldn't cost you more than a few cents, so it should be fine. And if you don't have one, we got you covered. So there is a bunch of keys available on this space bin here. With those keys, you are limited to using these mini and small embedding models, but these will be sufficient and are used by default in the workshop. Yeah, and I think that's mostly it. Please don't spam those keys too much because they are linked to my account, so I don't want to reach my credit limit too early. And that's it. Victor, you want to take over and quickly show the report? It's in private. So the repo is still in private for the moment. We're just working on making it public. If you have any questions that we can address in the meantime, that would be a good opportunity.
Yeah, maybe for the Stanford experiment that you showed,
Yeah.
where like they play it in the game.
Yeah.
So these agents, they decide also where to walk in the world.
Yeah.
How like do they make this kind of decisions? How do they have information about where things are in the world?
Yeah, exactly. So the question is how do the agents know where to go and have knowledge of the world in the little Stanford video game paper that we showed. So typically they have not a full complete knowledge of the world. They have their own memory and they have their own plan for the day. So for example, I don't know, there is a little, let's say, farmer agent and he wants to go to the field and plant a few carrots and harvest stuff. So he knows what he wants to do. And he has a limited peripheral area that he can feel in the environment and know what's in there. So when he gets close to another agent, he knows that the other agent is there. But it's not a full, complete knowledge of the world. Does that answer your question? Or not really?
Yeah, so they get this fed into their input in some way.
Yeah, they have an input stream that is based on their location, based on their position in the environment, etc.
Okay, so we will make the repo public. We currently, I think, lack administrator access, so I'll just share it on my personal account. If you want to go back to it later, you should go back to the link in the presentation slides. So you can go to this repo in Git, and you have the link here. Sorry?
Can you make it a little bit larger?
Yes. If everyone is ready, I can quickly go through the different notebooks and folders we have. So what you will find on the repo is those two folders. So in the notebooks, you'll find the exercises where you can fill the code with the examples we showed before that Gaetan showed in the slides. If you are struggling or you don't want to actually code, you can go in the solution folder where you have the 2 sessions notebooks already filled and already run and saved with the outputs. So you don't actually have to install any environment. You can also have a look directly at the end result. Sorry? No, so we work here not with requirements text, but with PyProject. But in the README, you have a summary of the workshop and then some requirements, which are the API key we discussed before and Python version. I think it would actually work with a previous Python version, but this one you should be sure that it will. And here you have the different way you can set up the environment, depending on what you use, if it's Conda or UV or virtual environments. So the official repo is now public also, if you want to connect to it instead of this one. So if everyone has access to the repo, I will quickly show some code structure, basically. So here in the notebook folder, you have the 2 exercise sessions. And as you can see, you have some explanations of the cells. Some are a repetition of what we presented in the slides. And you have at different steps some to-dos. And this one you should fill yourself if you're interested in doing a bit of implementation. So I will switch back to the slides. Gaetan and I can answer any questions, either on the agentic AI, agentic systems, or on the code itself. But what's included in the notebooks should be enough to solve any task on its own without referring to the slides.
So if anyone has any trouble installing the requirements or creating the environment or just running code in general or questions on what are the tasks at hand, feel free to just raise your hand and we'll come by.
Just generally, how long do you expect this solution that you put online going to live? How long is it going to be before it's rotten?
Before it's
Rotten.
Ah.
I mean, in general, LangChain, in my experience, I mean, I'm not a coder.
Yeah.
Means, you write a solution for clients, 2 months later, nothing works anymore.
So definitely the ecosystem of LangChain and agents in general is evolving very quickly. Things are getting, almost daily as well. Like things are getting deprecated quite fast. As long as you stick around with, like if you pin your versions appropriately, you should still be able to run the things in the future. But of course, there is no guarantee that in 6 months they will not have changed their API completely. Again, this is more of an example with a very simple concept, just to grasp the overall way of how to work with agents. But as to the implementation details, these are valid for now. Who knows in the future, of course.
Also, we tried to, for the second workshop, for example, second part of the workshop, with LangGraph, we tried to use the latest development in the library, So it should be up to date as much as possible and hopefully last a bit longer. How is it going with the first session? Yeah, do people need a bit more time? Do you want to take a break now, or? I got a few times a question about the RAG system, so I just want to come back to it to give a bit more details about how RAG usually works and how we implement agentic RAG in this case. So RAG, the retrieval with the vector database, what you do is basically that you, as Gaetan explained, you store documents and you have embedding a vector representation for similarity retrieval. So you will retrieve a document based on the similarity of its representation with your query. We don't go too much into the details, but basically you can have a lot of parameters that you tune. For example, you can store only short parts of the documents, chunks, because storing an entire book is usually not feasible or not desirable. Because here we use short news articles, each point is the full article, but usually you would split your documents into smaller parts. In classical RAG, what you often have is that when you ask a query, yes? So RAG could be an entire workshop in itself. Sometimes you can have some limitations in the file length because you need this embedding model. So a model that takes an input and creates a vector representation. And some models have a limited context length. But in general, when you do a query, for example, you do not want to have an entire book or PDF back. You just want to find parts of this document that are optimal. So this, in general, really depends on your use case. And this is a parameter that you should tune and test to see how best to chunk the documents for your RAG system to work as well as possible in your particular case. For classical RAG, you often have a user query. This query you use directly to retrieve documents, and then the query is given together with the documents to the LLM. Here we do RAG as a tool, so it's a bit more complex. The agent, by being provided with the tool, can decide to make the retrieval or not. And the agent, the LLM, will decide what query also to make. So this is not just based on your questions, it's based on the LLM decision. So this already is part of planning and taking actions in an environment. So as you can see here, that's why we have the small tool image. And the vector database was in classical RAG, you would have input, vector database and retrieval, and then LLM. And in the notebook in particular, through the system prompt, we push the agent to make the call for an example. And we also constrain the example to a single call by then using the model without tool access. But you could have a much more complex system where the agent, for example, will not make a call to the retrieval because it thinks that it's not necessary to answer the question, or could make calls in a loop. So, for example, you ask a question, it finds documents, it looks at the documents, and if the documents are not relevant, it can decide to then make another query. So already there you've got a lot of flexibility in what happens in your system. So that's what we're trying to show out. Just the ability for the model to take actions independently, but in a very simple case where you have a single retrieval call. Yes?
How do I determine to what extent the right space will be loyal to the document database that I've provided? Is this the temperature parameter?
So this is a more general problem with LLMs that sometimes you can call hallucinations, where a model will not always write an answer that's very grounded in the documents it retrieves. So again, for that, in practice, what you might want to do is first to tune the number of documents retrieved, because if there is too much context or too many documents, the model might lose some accuracy and could maybe just not retrieve the desired information. So that's why you do not want to just give the entire database, but you want to retrieve just relevant documents to help also the model. And again, in practice, what you could implement, and this goes back to the back and forth workflow that we've seen before, is to also have an other LLM that could check that the answer is indeed grounded in the documents. So this could be part of your workflow to add some reliability, to have a check, an additional check. Okay, so what we're going to do is quickly go through the first notebook to align on what's happening in it, maybe clarify some doubts that you could have, and then we'll move on to the second session, which is a bit more involved and presents LangGraph. Sorry. So first session, as presented by Gaëtan in the slides, first you define global variables, and you create a simple chat model. So a simple chat model with the chat OpenAI method. You then define a system prompt that will give instructions to the expected behavior of the model. You have here just a request, a didactic request that we defined. The example is an investment finance agent. Then in LangChain, how it works is that you have a list of messages. So as you can see at the first step, you only have the system prompt to define the behavior and the human message built with the request. So this would be identical to you sending a message to ChatGPT with ChatGPT having instructions of giving financial advices. Then you use the invoke method to get the response from the model. So here we display the initial response, which is very general, as you can see, from the standard LLM. Then we move on to the RAG system, the retrieval one. So this workshop is not that focused on RAG, so that's why we're going quickly over it. But as I said before, there are a lot of things you can tune in a RAG system. The base for it is to create the vector database here, a chroma vector database. This actually, this is local on your device, but it's a very few documents. For real use case, you'd like cloud storage with large database providers. Then you probably would want also to tune the vector storage. For example, if you have large documents, you want to split them in smaller parts to not retrieve 5 pages PDF from the database, but only the section you are interested in. So here we load the provided documents, the news articles. We create, So here, for example, you have an example of one news article, sorry, with the headline and the article. As you can see, it's very short. So we don't do chunking here. We store the whole document in the database. Here we create the vector store, and we create a retriever from the vector store. So the retriever is the object that you'll use to query the vector store. So you pass the query to the retriever. You can create it with different arguments. Here we only fix one, which is k, which is the number of documents you want to retrieve. But you can, as Gaetan said, also fix the similarity threshold, for example, for returning a document. And if the query doesn't find good enough documents, it could return none, for example. So here we do a simple query. So as you can see, it's text, and the text will be transformed into an embedding also, and compared to the embedding of the documents in the database. So all of that part is abstracted in the vector store and the retriever. So you never actually have to, and the model, when you provide it with the tool, never have to interact with the embedding representation. It's just a query as text, and you retrieve documents. So as you can see here, we fixed the number of documents to 3. So when I do this query, I get the 3 most similar documents in the database, or that have the closest representation to the query. Again, this should be tuned for practical cases. Here we're using a small embedding model. You might want to use an embedding model, for example, that is fine-tuned on financial news data. If you want more fine-grained representation, you might want also to chunk your documents to not include all of the parts that might be about very different topics. Then we create the RAG system. So as I said before, we don't have a simple chain of retrieval, providing the documents to the model and querying the model on the user request and the documents. So that would be retrieving documents from the user message, providing these documents with the user message to the model. Here what we actually do is to create a tool. So the tool basically, in this case, receives only a retrieval query and use the retriever to return documents. And here we inform the model in the system prompt that it has access to the database. For this example, we actually push it to use the database. But the goal of the tool is, in theory, to give it complete control over how and when to query the tools. So using bind tools from LangChain, we transmit the information to the model. So LangChain takes care from your tool method to inform the model about the tool name, what it needs to receive, and what it will return. So all this information is going to help the LLM decide when it needs to use the tool. So as I said, here we basically call the model with the RAG prompt and the same request. And the LLM will receive these messages in addition to the information about how to query the database, how to use the tool. And because we push it in the prompt to use it, as you can see, the first response of the model has no content, so no textual answer, but has a tool call, retrieval. So this is the tool. So it called the tool, and the arguments, as you can see, there is retrieval query. Because it knows to call the tool, it has to give arguments. It knows the only argument requested here is retrieval query, and it creates itself the query it wants. So based on the user requests about investing in the technology sector, it decides to call the database to retrieve documents that are similar to investment strategy technology sector 2023. So as you can see here, the model is responsible for deciding what to retrieve based on context. So this is part of the agentic framework, and LangChain helps with creating that. So here we verify that the response indeed contains tool calls. If it does, we retrieve the actual tool. from the list we defined, and the dictionary of names to function. This is a bit technical, but basically what you need to focus on is that we retrieve the documents according to what the model decided to do with the tool at hand. Then those documents, we format them here as a single text that we can then provide back to the model. So as an example, from the query defined by the model, we have these 3 documents returned. Then we rebuild the message chain, the message list. So the model actually doesn't have a memory. So when you, for example, use ChatGPT again, you have these sequences of messages. Because the model doesn't really have a memory, each time we call it, it needs to have access to the whole list of messages in order to have context. If you were to only send the last one, with this implementation, it would not know where the information comes from, it would not have the system prompt, it would not have the user request. So we have to give the message sequences for the model to have context. That's why we rebuild here the list. Again, in practice, you do not have to rebuild it fully. You could just add the last messages each time to the list and keep a list state. And that's how it's done, for example, in LangGraph. So you could have the first messages and do append RAG response. And then when you get the tool response, you also append it to the list. And I believe LangChain, or even the OpenAI API in that case, they provide some caching in some cases. So here, I don't know if it's used, but in theory, you do not have to recompute everything each time. You can also have smart caching, so the computations done on the first message are not repeated each time you call the model again. So here we call the base model. This is, again, just for this didactic case, because we do not want to have a second tool call. So this is just a constraint we put in this example to avoid having this looping behavior. But in some cases, you might want this looping behavior. For example, you might want to tell the model, if the documents you retrieve are not relevant for the query, make another one. Here we remove the tool ability basically by not calling the RAG model, but going back to the base model. And as you can see, these provide us with a response that is actually grounded in the documents retrieved. So that's why you see it mentions MERS and power growth, for example. So information in this response actually makes use of the 3 retrieved documents. And yeah, so important points, you can play around with the temperature. The lower it is, usually the more deterministic it is. So you usually do not want for factual and control environments or systems to have a high temperature. So if you want to have something in production, for example, you might want something more deterministic. So that's why we set here temperature to 0. But for example, for creative outputs, you might actually want more, a bit more randomness in the model generation. So this can be tuned. The number of documents can be also modified. Here we hard-coded it to 3, but you might want to play with that. You can also add that as a parameter to the model and let the model, the LLM, decide how many documents you want to retrieve on the fly together with the query. So you have a lot of freedom. And this example is just meant to introduce you to the concepts. And system prompt also is the main definer of the model behavior. So that's where you're going to give it a role, sometimes a personality, or some indications about what you expect it to produce as an output. But we'll see more about that in the second session. Yes?
So in the tool call,
Mm-hmm.
when you print out the tool call, there is a translation of the request into a tool call.
Yes.
What is actually doing that? Is that the system prompt or?
Translation of the, sorry, you said the request into the...
You call the tool and you display that. It's not the exact right request that gets passed in, right?
sorry, you mean here? So you have the RAG response and you have the content that's empty and the tool calls that contains a call.
I'm referring to the line below that you
This one?
investment strategy, technology sector 2020.
Yes.
That's not exactly what you requested, right? So there is a...
When you say what I requested, are you referring to here?
Correct.
So, okay, so let's focus a bit on that. So the request here is the one you addressed to the LLM. The LLM, by using the bind tools, has information about the fact that there is a database it can query and that it should write, it should create a retrieval query, right? And when you call it, with this user request, your model will decide how to query the database to retrieve documents to help answer this request. So it's not the exact same text, but that's what the model here, GPT-4o mini, that's what the model assumes is the most relevant document retrieval query to help with the user request.
Okay. And how would you influence that in the way you define the database?
Sorry?
How would you influence that? Is that in the way you would define that database?
So you mean how would you influence what the model decides to make as a call? Yeah, I think it can basically depend on the knowledge of the model about what's inside the database. You could also give some stronger instructions about what you expect as a query. So this is more about influencing the model behavior in the query it does. And so I would say mainly system prompt or in the tool description. And or even in the user request, you could say, I expect you to do research on this specific topic. So there are a lot of ways that you could influence what the LLM will produce as a retrieval query. And again, you could give it freedom to do multiple ones to find the best documents if the first retrieved ones are not useful for answering the request.
Okay, short question. Why the year was added? It was just the actual year when the example was executed.
You mean 2023? This is the model, because I think the GPT-4o mini model we use has probably knowledge shortcut to 2023. So when you ask for how to invest, it tries to be very actual, very, yeah. So it just, I think it assumes it's 2023 and thinks about.
I think this is just a problem of a year, because when you have newer documents,
Mhm.
and this is the sense of the whole, that you have, for example, documents of 2024 or 2025.
Absolutely, yeah.
So here, it would be good to tune the
Yeah.
question a little bit more.
Mhm.
But okay, it's only next
Right, you could, for example, for that, you could give it in the system prompt. You could say, the date is 2025, and you have access to documents ranging from 2013 to 2025. You could also have some requests that have nothing to do with any time period, maybe more time invariant documents. Could be anything, I mean, like cooking lessons or something that does not depend on the actual period. Yeah, so I think lots of ways. Also, you could, for example, here, you could add in the messages, you could add a system message also. I don't know exactly what message would be used, but information about today is the ta-ta-ta, and just, yeah. So lots of ways again.
Last one over there.
Yeah, last question, and then I think we need to move on. Yes, please.
I actually have two questions. So, really quickly, the first one would be, could you give us to have a clear idea for the tool? Like, so,
Sorry, can you repeat? I'm not hearing you. So,
so could you give us to have a clearer idea of the tools? Could you give us some examples, apart from the retrieval, what tools could be used?
So a few other examples. You can basically think as a tool as anything that the model can decide to use to have some interactions with external environments. When I say external, it does not mean to external to your, for example, computer or a server. It just means external to the LLM itself. So here it's access to a database, but it could be web research, it could be code execution. It could be calls to a different API. So you are basically free to define. It could be a calculator. It's just something that the model has information about how to use and can then call to extend its capabilities. Yeah.
Would you think this would be the right way to go, or would it be to append the messages one after the other and have a full discussion every time you want to send the...
So if we go back to here, for example, what you have is the system prompt defining the behavior, the human message. The response here, for example, in this case, it would be the tool call, so the model knows it made the tool call before, and the documents. And here the documents are not summarized. And you could, in theory, have a continuation of a discussion based on the full document. About summarization, it might make the calls a bit more lightweight. Also, maybe for the user, it might be easier to grasp the main elements, but you might want to have another model verifying that the summary is of high quality, for example. So it basically all depends on your use case. I don't think I can give a strict answer, but we'll see in the second workshop some ways to approach that. Okay, so let's move on. I think time is running a bit short. So again, I'll quickly present some slides about what is in the second notebook. So this is what we want to implement today. So this is beginning to be already a complex workflow, but we try to introduce many interesting concepts basically that can be implemented in LangGraph in one example and make it as easy as possible to learn it and to understand the different parts. So what we are going to do is use LangGraph, which is it's a framework built by LangChain to have these workflows that we presented at the beginning of the workshop, and to define edges and nodes, basically, and the communication flow between the different nodes. In this practical case, what we're going to have is a client interface agent, so that's take the role of the orchestrator, and it receives client requests and must answer the client and define a research plan that will be sent dynamically to the workers. So we do not have a fixed number of workers. This will be created on the fly based on the research plan that is designed by the orchestrator, the CIA agent in this case. The workers, the Bloomberg Research Agents, the BRA for short, they are similar to the case you saw in the first notebook with the RAG. So their task will be given a task defined by the CIA to do research on that task by querying the Bloomberg database that you created before and summarizing the documents. So this, I think, answers a bit the question from before. Each of these workers will be able to retrieve by itself different documents for different tasks. And when those documents are retrieved, to make it more easy for the synthesizer to create a final output, they basically summarize the main findings that help answer the research task they were assigned. And the last agent, the research synthesis agent, RSA for short, will receive all these research summaries and will combine them into one final output answer to help answer the client's request. So first concept basically of LangGraph is that it has a state that is used to share information between the different nodes and to keep basically track of, for example, the messages. Here we have two attributes that we define. So the messages that will keep track of the communications throughout the workflow, and the analysis that will collect the analysis of each BRA agent. So this is, as you can see, the workflow state, the custom class that we created. But basically, you might want to add any attributes that could help with your particular use case. Then you have to actually build the graph. So here, the nodes functions are not yet defined. But how to do that is to create a state graph instance. And you define an entry point. So that's where the workflow will begin. And then you can add nodes. The classical way to define the edges used to be after, or I mean at the same point, at the same time as defining the nodes. You would also use the graph builder to define the edges, so how the information flows in your network, what node connect to what node. We will use here some novel release from LangGraph from December that does not require anymore to define the edges at building time. I will present that just after this slide. So another concept that's useful also, which is in the same vein as the binding tools, is the structured output. So you can use Pydantic to create these base model classes. And these classes, as you can see here, we define a research task and the orchestrator decision. So you give them documentation, you give them a few properties, and you give these properties type hint descriptions. And basically from all this information that's contained on this slide, you can then constrain your LLM to produce an output that will actually be a class, an object of these classes. So as you can see from the base model, you use with structured output and you give your class. And why I'm saying that it works a bit like binding tools is that basically from this, the model, when you call it, will receive all the information about what you expect as an output, the fields, the types, the descriptions. And you do not have to specify that, for example, in the prompt or in your request. And in addition to that, LangChain will help parse the answer to not return just a string with the correct outputs, but return directly a class object. So this helps a lot for customizing the output and have some reliability, reproducibility into your workflow. So I was talking about edges in the workflow, in the graph. So this is now a way you can do it. It's using command. So what command does is basically that instead of having these functions that define nodes and then define the edges separately, you can directly define the communication flow in the node function. So as you can see here, so some of the main elements, it's the type hint at the top. So here, so you return a command, and here you give some information about the possible next nodes. So here, for example, this is the orchestrator node, and the next ones will be research or end. Maybe something I should specify that there is a difference between your function name and the node name. So you have to give string labels, basically, string names to your functions, to your nodes. I believe it's not mandatory, but this is common practice. So as you can see here, the orchestrator will receive the state. So this is what we want to share between the different nodes in the graph. You will have the invocation of the model on the request and the existing messages in the state. And this will be a structured output thanks to the constraint we established before. So we know that the orchestrator output will follow these classes. And here, so this is a bit tricky. The first node, because it's basically defining workers on the fly, is a bit more difficult than the other ones. So in the notebook, I think you should spend maybe a bit of time to make sure that you understand the different parts. But as you can see, it returns a command. And in the command, you have the update field that will give information about what you want to update in the state. And the following nodes, basically, in classical cases, will receive this state with the updated values. But in this case, goTo, instead of returning a string, as you can see, it goes to end. So end is a string, actually, and it goes to it if the user's query is not in scope for the model. So for example, if you would ask the model about the weather, that's not part of what we wanted to do. So here, as you can see, goTo would be equal to end, and you'd finish the graph. But what we do in this case for the orchestrator is return a list. So by returning a list, you go to multiple nodes at the same time. And here we add another concept. That's why I'm saying it becomes quickly a bit difficult, but the other nodes will be easier. We use send. So send basically goes to the research node, but instead of giving it the state, as it would by default, here you specifically give it a task object that comes from research tasks. And research tasks, as you can see, it's a list of research tasks. So each of the research node will receive an object of this class, which contain a topic and a description. So maybe just if you, let me know if it's clear, because I know this is a bit heavy, but you won't have to reproduce that, it's already filled, and the other nodes will be easier. But are there some concepts you want me to focus or explain again? Yes?
LangGraph is a part of the LangChain, or is completely separate library?
So it's built by LangChain, so it uses a lot of similar syntax and methods. For example, the invoke is very common. I think you could, in theory, leverage other libraries behind it. For example, here, this would be your node function, but here you could use a completely different library to call the model. For example, that does not need to be a LangChain model. That could be something completely different. You could even not use LLMs. I mean, you could use LangGraph to do the deterministic processing, for example. So the important part is really this sharing of the states, this definition of nodes, and now with command, the communication flow defined in the node itself instead of being defined externally. Yes?
Very high-level question. Where is the learning taking place?
So here, there is no learning. Those are pre-trained models with tasks assigned to them. So this is really a workflow where you want to achieve a goal, and the model tries to answer it. So it's comparable to, for example, ChatGPT, where you chat with it. So they can train the model on data, but during a chat, usually it's not learning anything. It's just answering to questions.
When you say it tries to achieve a goal, like it's the number of those agents,
Mm-hmm.
where is it learning to? The goal is always like a current state of the target that you're trying to reach.
Yeah, so goal again, when I say goal, here it's basically, let's say, the user request or a goal you define in the system prompt. And the way it tries to achieve this goal, basically, that's why it leverages Gen AI, and that's why we're coming to this kind of systems today, is because the model is trained enough, good enough, that when you request something from it, it can decide that, for example, it needs to separate your request into multiple steps to best achieve it. So it's not learning, it's planning, basically. Yes? I mean, I guess you could, in some cases, create some learning in your workflow. I think the interest of workflow is also to have something that's well-defined and controlled, so you might not want to actually change the model a lot when you use it. And also training a model is sometimes difficult. You could, I think learning is a bit hard to define. You could, in theory, have a model that will look up information online to learn new information, but that's not learning in the model itself. It's more learning through context about novel information. Sorry? No, in general, I don't think you want to mix fine-tuning or training the model and having a system running. So you can do what's called in-context learning, which is the model acquiring novel information, for example, through retrieving documents in a database that are private company documents that it has never seen. And from there, it can learn new document, but it's not learned in the model itself. Yes, and yeah.
So somehow related, so how do you evaluate the workflow so that you can, for instance, change prompts and get better results?
So that's a whole topic. It really depends on your use case, and there are some libraries, also for example LangSmith, that will help with monitoring what's happening. So you can have a look and you can try and tune the prompts. You could try to leverage LLMs themselves by asking an LLM to give some feedback on an output. This is a whole different topic. I won't go into details too much, but we can discuss it at the end of the workshop. Yeah, maybe one last if it's very quick.
It's just about the fact you said that research agents will be created, like deep data.
Yes.
What happened with that go-to with the list comprehension here? With the code?
Yeah, so the list comprehension is basically that here we define, the output that we want, and as you can see, the output is a list of research tasks. And we tell the model that it will be a list of research tasks to be completed that must contain a topic and a description. But we do not give a priori a number of tasks we want. So this is the first node, the CIA agent, as we call it, to decide how many tasks it defines. And then by extracting the list of tasks from the output, you return in the go-to a list of nodes that you go to next that each receive a different task. So this is the on-the-fly generation of different nodes. But all those nodes are hard-coded in the research function, but we go through a dynamic number of them based on the number of tasks returned.
Yeah, that's the thing. So if you like code, are you going to define like 5 nodes research access?
So the number of nodes and LLMs called are defined here. And the number of tasks, as you can see in the prompt in the notebook, we say a short list. But the interest here is to leave this decision to the model of planning how many tasks it needs to achieve to help the user. But you could also, that's something you can tune either through prompting by saying, giving more information about what the task needs to contain, or you can hard code it by, for example, having a predetermined number of nodes that it can go to next and predetermined tasks.
I guess we're going to see it later. I was meaning like what the graph is for.
Okay, that's in the notebook, so we will go through it at the end. I think we just need to move on a bit, but you will see that. So here, this is the graph example. So as you can see, there is the orchestrator. So here, indeed, what we show is 3 workers, but there are not predefined number of them. So when you print the graph being built itself, it will show up as a single node. But in theory, during execution, you can have 3, you can have 5, you can have a flexible number of them. And each of these workers will have the access to the database in a similar way to the one you defined in the first notebook. And then the output will be synthesized to return the user with an answer that's satisfiable and that can be based on these different steps. So this is contained in the second notebook. And again, there is a lot of information about the different steps. The first parts are pre-filled. For example, the kind of complex orchestrator node is predefined. And the other ones you can work through, and Gaeta and I will be in the room to help. Time-wise, I think we give maybe 30 minutes or so.
20, 30 minutes. And then
yeah. And then we will probably start going through the solution in around 30 minutes to leave a bit of time also for questions. Okay, so we will start going through the solution. I'm sorry we're running just a bit late, but I will stay afterwards to answer any questions or chat if you want. So in solution 2, so we are implementing this multi-agent system that we presented in the slides. So the beginning part is, again, just global configuration and variables. So this is very similar to the first notebook with the model names, for example, number of retrieved documents. So we will quickly go through that. Again, here you create the vector database and the retriever. And here you recreate the retrieval tool. Quick notice, you could also have the retrieval as a node in your graph. You could, instead of having it as a tool, you could tell the model that it can decide to go in the retrieval node and then do the retrieval in the retrieval node. There is a lot of flexibility. There are many ways to achieve the same goal. And this is all, in general, personal preference. And here we wanted to show how to use tools in particular. So that's why we did retrieval as a tool and gave the tool binding to the model instead of having it as an external node in your system. So here again, we just show once more the architecture we're going to be building. So orchestrator with the CIA agent in it, the different workers with the BRI agents that, as you can see, have this tool access from session 1 to query the vector database, and the synthesizer, RSA, that will, from their research, generate a final answer to the user query. So here we define the graph states that I presented in the slide. So this is used to share and transmit modify information between the nodes during the workflow execution. And we make it very simple in this case, so just messages, which will be the list of all the messages that we will append during the discussion, and analysis that we will use to collect the analysis from the dynamic number of worker nodes on the fly. So here, quick notice also, we use annotated. So this allows us to determine how this will be updated in the workflow. So instead of having, for example, to retrieve the messages and append a new one and return the whole list, you can then, thanks to this method, in the node, only return the last message. And this will give information that it does not erase your attribute, your values here. It will be added to the list. So this helps make clear how these variables, how these fields, basically in your states, will behave throughout the execution. And also it helps by alleviating the need to do yourself the appending to list operation in your node. So first agent, we constrain the outputs. Again, this is, we wanted to show how this works in LangChain. So that's Pydantic, where you give all the information about what the output is, what the fields are, the type of the fields, description of the fields. And then you can provide your model with that. Oh, I'm sorry, I'm in the exercise 1. I think I'll cheat and go to solutions directly. I would love to do the exercise, but yeah, we're a bit short. Right, so here, basically you structure the output of your LLM with orchestrator decision class. So your model will receive all the information contained in this cell. And it's a bit similar to bind tools. You basically do not need to do that, for example, in the system prompt, and you do not need to parse yourself the answers. So this is provided by LangChain. And this helps, again, make clear what you expect as an output to the model, and helps a lot in having consistent and reliable outputs from it. So as a prompt, we ask it to have a look at the user request, determine if it's in scope. So this will be indicated in the in scope boolean, and produce, if it is in scope, a list of research tasks that contain a topic and a description, and that will be sent to the research nodes. So this helps also, as you can see, then in the node function, this structured output helps also sometimes with the communication flow, because if the model puts false in the in scope, for example, I don't know if you ask about the weather, you can directly end the execution of the graph. You go to end and you will have an answer in messages. The response field, that will be, for example, I'm sorry, I'm a financial analyst and not, I cannot help with the weather requests. But if the model determines that the question is in scope, thanks to the system prompts and the structured output, it will produce a list of research tasks that will be contained in the research tasks field of the structured output. So here I just want to quickly go over that again because it's a bit tricky, but go-to is often a single string. Here, one of those two. But here we want to generate multiple subsequent calls to research nodes, so we create a list. And the second tricky part is that instead of using the default behavior of having the worker node receive the state, we explicitly send a task as an input. Default behavior would be it receives the shared state. So this node is kind of the most complex one in the system, so that's why it's already implemented. But what will happen is based on the CIA decision, you will have a flexible number of research nodes, worker nodes, that will each receive a research task input and achieve it before sending all the responses to the synthesizer. So for the Bloomberg Research Agent, we will not spend too much time because this is almost identical to what we did in session 1. So basically this is a function that receives, as you can see, not the state, but a research task. And that's why we explicitly send a research task object with send, and then goes to synthesizer at the end. So what it does is extract the topic and description from the task object, research task object, create a string, and then you will call the model with retrieval tool on the system message and the task string. So here, for example, it's I put human message. This is a bit up to you to decide. So human message would make the model believe that the research task is actually requested by a human. I don't think it would change too much if it was an AI message. Again, this is kind of up to testing and evaluation. So you get the output, again, through the prompt definition and simple example, you should expect tool calls, and you should, in theory, have a single tool call to the retrieval tool, as in example 1. So this is all identical to example 1. And then you will append this tool call and the tool message to a message list. And then, again, we invoke the base model to have a bit more constrained didactic example without subsequent tool calls. And as a return, as you can see here, the goto is a single string because we will want to go to synthesizer and have it receive the workflow state, basically, so default behavior. And we update the analysis field of the state by giving it the content of the answer. So this is a textual answer, basically a string. And here we have to give a list because if we quickly have a look at the state class, here, analysis, it's a list of string, and it's updated with operator add. So you need to give a list that will be added to the list. That will be concatenated, basically. And then from there, all the worker nodes, they go to synthesizer. So the research synthesis agent, RSA. And this is a very basic one. So that's what at the beginning I said that we would use agent sometimes when it's just a prompted or like role-given LLM. And this one basically will receive all the research from the different worker nodes and generate a final output. So as you can see, the description is that given all this research, just make it an answer to the user query, the user request. So it receives the state, as default behavior, and then it will go to end as deterministic next node, basically. As you can see, we extract here the analysis, the list of string research tasks answers from the previous nodes. We make it a single string. Again, I think we could, in theory, make it multiple messages. This is flexible and might want to be tuned. But here we basically just create a single string based on the flexible number of analyses we receive. We give the prompt, the list of existing messages. In this case, should be user requests, CIA agent answer to the user, and then the complete analysis. Then we use the base model to answer to that. And we go to end and update message with the RSA output. So here, for example, like these messages, AR messages, we give them to the base model to answer, but we do not add them to the state messages. So the actual research answers from the research agents will not be returned in the state messages. This means that basically all the research, for example, is kind of happening at execution time, but in the background, and you do not get it back from calling the system. This is graph building. So as you can see, you use the state graph class. You add an entry point, you define your nodes, and then you do not need to define your edges anymore because this is now done thanks to command directly in the node functions. You then compile the graph. You can display it. So as you can see, we enter orchestrator. We can go directly to end if the question is not in scope, or to worker with a single one shown here because the number is not predetermined. But in practice, during execution, you might have multiple of them based on orchestrator decision of research tasks, synthesizer, and end. And then you can make a request, invoke the application on this request. So you will add this request to the messages. And as you can see here, we displayed some elements during executions. So we see that we receive a client request. We see the response from the CIA. Then we see for each research node, we see the research tasks that they receive from the orchestrator. We also see the documents that they each retrieve. So here, for example, we didn't display the retrieval query they make, but that's also something you can do. So as you can see, they retrieve different documents, sometimes the same ones, because there is some overlap and we have a limited number of documents. And then we see the synthesizer that received research from 4 browsers. So then you get this final state that's returned by the app invocation. And we extract the last message, which basically will be the synthesizer answer. We print its content, as you can see. This is a much more extensive answer. This is based also on some retrieving information, for example, the HP shares or Apple. So all of that is basically built from synthesizing the research for the multiple agents by the last LLM. And yeah, that's it. That's the end of the workshop. Some tips. So be sure to define well the role of each of the agent if you want some consistent behavior. You can additionally add some structured output thanks to LangChain. And then obviously, because it's LLMs and you are chaining a lot of them, it's hard to have deterministic results. So you should, in most cases, be sure to monitor the behavior a lot. There are frameworks like LangSmith that help with that, which is also done by LangChain. And now maybe we have still a bit of time to answer some questions. And I think I hope you appreciated the workshop. Thank you.